Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends, to your younger brothers and sisters, and to your friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies as part of your preparations to engineering life, then please don't forget to subscribe.
Let's now have an expression for the product of inertia. Before we do that, let's have the preliminary discussion on the transformation of moment of inertia, which is important in finding the orientation of the area in such a way that we can find the maximum and minimum moment of inertia. But it is not focused here. What we focus here would be the expression for product of inertia for various shapes and sections. So I sub x, I sub y, and I sub o are all positive and of different values depending on the axis chosen. Ix and Iy can also be equal if the orientation is such that it is symmetric with respect to the x and the y axis. And point O would be the centroid. There is a need to determine the maximum and minimum moments of inertia of areas by finding that orientation of axes producing those values by introducing a new concept, which is the product of inertia. So in this video, we will focus first on deriving formulas for various orientations of common shapes and figures in deriving the product of inertia of that particular shape. The concept of product of inertia enables us to determine the amount of rotation of axes locating these maximum or minimum moments of inertia. So the product of inertia is given by the expression integral of x, y, dA. So this is the product of inertia with respect to the x and y axis and is defined by the integral of x, y, dA. So in this figure here, x is the x coordinate of the centroid of the element of the differential area, because the differential area may not be this point size element. It may be a horizontal rectangular strip or vertical rectangular strip depending on the situation. But this formula here is the formula for the general expression for product of inertia, but you are reminded that x is the x coordinate of the centroid of the differential area. Unless the differential area looks like this, then x is just x, y is just y. But for other situations where we select or opt to select horizontal or vertical strips, then remember that x is the x coordinate of the centroid of the elemental shape. Y is the y coordinate of the differential area or the elemental strip. The product of inertia of an area can be positive, negative, or zero. So here is the situations where we expect positive product of inertia. So in this case, the product of inertia is positive. It's because most of the areas lie in the first and in the third quadrant. So comparing the areas in the first and in the third quadrants, where in the first quadrant both x and y are positive, and in the third quadrant both x and y are negative, so this gives us positive product of inertia. And comparing to the areas lying in the second and in the fourth quadrants, where the coordinates x and y will have negative opposite signs, that's why the product of inertia would be negative in those quadrants. This is the situation where we have negative product of inertia because most of the areas lie in the second and in the fourth quadrants. And finally, we have a moment of inertia, product of inertia, which is zero when when there is when the area has at least one axis of symmetry. At least one axis of symmetry, like this section here, the area is symmetric with respect to the y-axis. So if there is an element in the first quadrant where x is positive and y is positive also, there corresponds a differential area on the second quadrant where x is negative and y is positive. So that's why the product of inertia of a section with respect to an axis xy through the centroid, when this axis, when one of the axes is a symmetric axis, then it is zero, even if both axes are symmetrical with respect to the area. So the product of inertia of an area is zero with respect to x and y axis when one or both of these axes are axes of symmetry. I will now discuss parallel axis theorem for product of inertia of areas, or this is called the transfer formula for product of inertia of areas. So let's consider the region shown, and our element would be dA, and the distance of dA from the y-axis is x, distance of dA from the x-axis is y, and we have the centroid at C, centroidal axis x prime and y prime, and therefore the distance of dA from the centroidal axis would be x prime and y prime respectively. So by definition, product of inertia Ixy or Pxy in other uh, topics, I'll prefer P for symbol for product of inertia, especially in finding the maximum and minimum moments of inertia. That would be a few videos later. So Ixy equals integral of xy dA. Remember that x is the x-coordinate of the centroid of the differential element, and y is the y-coordinate of the centroid of the differential element. So in this case, x is barred x plus x prime, and y is barred y plus y prime. So Ixy equals integral of barred x plus x prime quantity times barred y plus y prime quantity dA. So expanding, Ixy equals barred x barred y integral of dA, then plus, because barred x and barred y are constant, plus barred x y prime dA integral. So take note, barred x is constant, so we only evaluate integral of y prime dA, then plus barred y integral of x prime dA, or x prime barred y integral of barred x prime barred y dA, and take note that barred y is constant. Then we have integral of x prime y prime dA. We note that barred x is constant, so we can put this before the integral sign. Of course, integral of barred x barred y integral of dA is just area barred x barred y. This one, integral of y prime dA by the first moment of mass, this is simply area times y sub c. That means that y sub c is 0 because it passes through the centroid. So this expression will just be 0. Then integral of x prime dA, barred y is constant, is area x sub c. And again, x sub c is 0. That means it passes through this. So this integral would be 0. Then integral of x prime y prime dA is simply because it is referred to c, this is simply the centroidal product of inertia, which is equal to I barred xy, I barred xy, or I sub c xy. So this is 0 because this is supposedly area y sub c, and y sub c is 0. This is barred y. Integral of x prime dA is area x sub c, and x sub c is 0 also. It passes through the centroid. So therefore, this is 0. That is also 0. Simplifying, ixy therefore is barred x barred y area plus I barred x prime xy. Lastly, ixy equals I barred xy, or the centroidal product of inertia, plus area barred x barred y. So take note that this transfer formula, or the parallel axis theorem, is synonymous or looks the same as that of the parallel axis theorem for moment of inertia of area. Remember, Ix is I barred x plus area barred y square, and Iy equals I barred y plus area barred x square. So it looks the same. Then we can also say that Ixy, or P sub xy, is Igxy plus area barred area xgyg, or simply Ixy is equal to I sub cxy, or centroidal product of inertia, plus the area of the region, then x coordinate of the centroid of the region, y coordinate of the centroid of the region. So let's have this problem as an application in determining the product of inertia. Ixy of the rectangle oriented as shown by integration. Check establish formula by parallel axis theorem. So if this is the orientation, then we'll have a expression for product of inertia. Now, if unlike moment of inertia, where moment of inertia with respect to the base is bh cubed over 3, if it is oriented in the second quadrant, it is bh cubed over 3. If it is below the x-axis, whether it is in the third or fourth quadrant, the moment of inertia with respect to the x-axis is always bh cubed over 3. But for product of inertia, it would change as presented here. So let's consider a horizontal strip for our solution. The length of the strip is b because the shape is a rectangle. The distance of the centroid of this strip, because for our expression integral of xy dA, the distance of the centroid of the strip from the y-axis, which is supposedly x in the formula integral of xy dA, is b over 2. It is constant, and the vertical distance of the centroid of the strip from the x-axis is y, changing variable, and the thickness is dy. So again, the x-coordinate of the strip is b over 2, and the y-coordinate of the centroid of the strip is simply y. And the differential area is the area of this elemental strip, which is b times dy. So Ixy, which is integral of xy dA, is equal to integral of quantity b over 2 times y times b dy for the area. So b square over 2 integral of y dy is y square over 2. So b square over 2, y square over 2 from 0 to h. The variable of integration is y because of that differential y there. So this is b square h square over 4. Lower limit 0. So that's the product of inertia of a rectangular area with respect to the xy axis, and if the rectangular area is oriented as shown. Then if we use the parallel axis theorem, xy equals I barred xy plus area barred x barred y. Since the rectangular area is symmetric with respect to both axes, centroidal both axes, then this is just 0. And barred x is b over 2. The centroid of the rectangle is here, so that is b over 2, and the barred y is y over 2, h over 2 rather. So Ixy, let us say unknown, equals 0 plus bh area of rectangle b over 2 times h over 2 for barred x and barred y. So the centroid is here, b over 2, that's h over 2. So simplifying this, it will give us the same answer as b square h square over 4. So when the rectangular area is oriented in such a manner that the edges are coincident with the x and y axis, or in the third quadrant like this, the product of inertia with respect to xy axis is same positive b square h square over 4, because in this orientation here b x bar is negative b over 2 and barred y is negative h over 2, so the product of negatives is positive. The area is the same. But if this oriented in the so that the rectangle lies in the second and in the fourth quadrant, barred x and barred y will have opposite signs. Therefore, the product of inertia with respect to the xy axis would be negative of this formula. So negative b square h square over 4, and also here negative b square h square over 4. So next problem, level 106, determine the product of inertia of the right triangle shown letter A with respect to the x and y axis, and B with respect to the centroidal axis parallel to the x and y axis. So the triangle is oriented in this manner. Remember that for different orientation, the product of inertia will either be same sign, positive or negative. So for the solution, let's have that strip. The length is x of the strip. The distance of every element of that elemental strip from the x-axis is y, and the thickness is dy. So the differential area is x times dy. Remember that the centroid is here, and that distance of the centroid from the y-axis is x over 2. Its distance from the x-axis is just y. So from ixy equals integral of xy dA, so x is not x, it is x over 2, because the x coordinate of the centroid of the element is x over 2, while y is just y, and dA is the area of this strip, which is x times dy. So ixy equals integral of quantity x over 2 times y times x dy. The variable of integration again is y, that's why the limits would be from 0 to h. Then we express x in terms of y by similar triangles. This is h minus y. So we have x as to h minus y equals b as to h. So ixy equals 1/2 integral of x squared y dy. Then by similar triangles, so that is h minus y, x as to h minus y equals b as to h. So that means x is b over h times h minus y, quantity h minus y. Substitute here. So x squared equals b squared over h squared, quantity h minus y, quantity square. We then substitute the value of x squared here. So ixy equals 1/2 of b squared over h squared. So b squared over 2h squared integral of x squared, which is h minus y quantity square times y dy. Before integrating, we have to expand. So ixy equals b squared over 2h squared, quantity integral 0 to h of h squared y minus 2hy squared plus y cubed, because this is h squared times y, so h squared y minus 2hy, the middle term, times y, so minus 2hy squared. The last term is positive y squared times y, so y cubed dy. Integrating, we have b squared over 2h squared times quantity h squared y squared over 2 minus 2hy cubed over 3 plus y to the fourth over 4 from 0 to h. So we don't mind the lower limit. These terms are like terms. 1/2 of h to the fourth minus 2/3 h to the fourth plus 1/4 h to the fourth times b squared over 2h squared. So that would be in terms of b squared h squared. So ixy equals b squared over 2h squared times quantity h to the fourth over 2 minus 2 thirds h to the fourth plus h to the fourth over 4 minus 0. So ixy equals b squared h squared over 24. So the reason the reason why it is positive because the area lies in the first quadrant and both x and y there would be positive. Then if the with respect to the centroidal axis, since most of the areas lie in the second and in the fourth quadrant, when we compute for moment of product of inertia with respect to the centroidal x and y axis, we expect that it is negative. So same for this orientation of the triangle, product of inertia ixy would be same b squared h squared over 24 for this orientation like this one in the first and in the third quadrant. In the third quadrant, both barred x and barred y would be negative, so the product would be positive. For B, by parallel axis theorem for product of inertia, ixy equals I bar xy plus area barred x barred y. Barred x is b over 3, barred y is h over 3, and ixy is b squared h squared over 24, which we have just derived. So b squared h squared over 24 equals I barred xy plus area 1/2 of bh times b over 3 times h over 3. So these are like terms. 1 over 24 minus 1 over 18 will give us a negative value of negative b squared h squared over 72. So you have to familiar and memorize this so that when the shape, the region con consists of different shapes and a triangle is present and in this orientation here, then we can use the transfer formula or the parallel axis theorem for product of inertia over here. Now when the triangle is oriented in this manner, ixy would be negative b squared h squared over 24 and I barred xy would be positive b squared h squared over 72. It will be positive the product of inertia with respect to the centroid. And the explanation, because most of the areas we lie, if this is the centroid, most of the areas we lie in the first and in the third quadrant with respect to the centroid if the triangle is oriented in this manner, opposite to that. Level 107, determine the product of inertia of the quarter circle shown part A with respect to the x and y axis, and B with respect to the centroidal axis parallel to the x and y axis. So here is the orientation of the quarter circular area. That's the location of the centroid. So let's have a horizontal strip, and the length of the strip is x distance from the y-axis, so that's x. Distance from the x-axis is y, and the thickness is dy. So that the centroid of the elemental strip would be here at x over 2 from the y-axis and y from the x-axis. So ixy for our solution equals integral of xy dA. Remember that we will not use this directly unless our element is a point size element. So x is interpreted as the x coordinate of the centroid of the element, which is x over 2, and y is just y, and dA is x times dy. So ixy therefore is integral of quantity x over 2 times y times x dy. So ixy equals 1/2 integral of x squared times y dy. Our variable of integration is y again because of dy, and limits would be from 0 to r. Now from equation of circle with center at the origin, x squared plus y squared equals r squared, or the other way is by Pythagoras theorem. Imagine we have here x, we have here y, the dimensions of the right triangle, and the hypotenuse is the radius of the circle. So x, that is y, and that is r. Therefore, x squared plus y squared equals r squared, or simply x squared equals r squared, hypotenuse squared, minus y squared. So ixy equals 1/2 integral of from 0 to r of r squared minus y squared times y dy. So ixy equals 1/2 of quantity integral r squared y minus y cubed quantity dy. So ixy, by integrating, ixy equals 1/2 quantity r squared y squared over 2 minus y to the 4th over 4 from 0 to r. So since these are like terms, we have 1/2 r to the 4th over 2, quantity r to the 4th over 2 minus r to the 4th over 4 minus 0. So 1/2 minus 1/4 is 1/4. So we have 1/4 r to the 4th divided by 2. So ixy is r to the 4th over 8. It is positive because the area lies in the first quadrant. Now applying the transfer formula for product of inertia, the location of the centroid for quarter circular area is, if you can remember, 4/3 4r over 3 pi, and from the x-axis 4r over 3 pi also. So from the y-axis 4r over 3 pi, from the x-axis 4r over 3 pi. So both barred x and barred y would be equal to 4r over 3 pi. So ixy equals I barred xy plus area of quarter circle barred x barred y. So r to the 4th over 8 equals I barred xy plus pi r square over 4 quantity 4r over 3 pi times 4r over 3 pi. So take note that this left side term is like the second term of the right, r to the 4th. So I barred xy is quantity 1/8 minus, cancel for 4 over 9 pi. 1/8, quantity 1/8 minus 4 over 9 pi r to the 4th, and in decimal that is negative 0.016471 r to the 4th. It is negative because with respect to the centroid, most of the areas lies in the second. This is greater, and this one than these two areas here. So that's why it's negative 0.016471 r to the 4th.